Good morning, everyone. My name is P. Mohit, and in this operating systems complex engineering problem, I have my topic distributed deadlock detection and recovery system for efficient solutions for network resource management. So, in this, we will be seeing introduction to distributed deadlocks, deadlock detection techniques, deadlock recovery mechanisms, and practical considerations and future detections. So, first, let us introduct to distributed deadlocks. Okay. So we have understanding deadlocks in distributed systems. Okay. So yeah. Yep. Okay. So definition of deadlocks. So deadlocks occur when distributed processes wait indefinitely for resources held by each other, causing system halt. So this is almost similar to system batch or batch processing, where each batch have to wait until the previous batch has been completely executed. So this cause of deadlocks in distributed environments contains resource contamination, circular wait, hold and wait conditions, asynchronous communication delay, cause deadlock in distributed systems. Now, in this characteristics, unique and distributed deadlocks, which involve multiple nodes with partial information, asynchronous communication, and lack centralized control. Now, importance of deadlock detection and recovery. So now, for this, we have to detect our deadlock and we have to recover this. So first is impact on system performance, and second is challenges in distributed settings. So on the first one, so in this distributed deadlock, significantly degrade system throughput and response time, and necessitating efficient detection and recovery mechanisms. We have challenges in distributed settings where distributed deadlock detection faces challenges like lack of global state, message delays, and resource asynchronization. Next, coming to the deadlock detection techniques, we have first is centralized deadlock detection. Now, to detect this deadlock, we have algorithm overview, advantages and limitations, and use cases. Let's call the first one is algorithm overview. We have centralized algorithm uses a single coordinator to collect global processes and states and detect deadlocks efficiently. Now, the advantages and limitations are first, let's go on the advantages first. So, it simplifies detection with a single coordinator, reduce message complexity limitations. We have single point of failure, scalability issues in large distributed systems. So, this is only single coordinator. So, for 3 to 4 batches, for it's okay. If it contains more than 4 or 5 batches, it may become a time complexity might be a little bit high. With use cases, we see that centralized detection suits small networks, reduce complexity, but risk in single point failure, sufficient for limited and resource conflicts. Next, we use have distributed deadlock detection algorithms. We see have path pushing algorithm, edge chasing, and comparison of algorithms. Let's see compare between these two. They have the common two things. First is path pushing algorithm. We see that it detects distributed deadlocks by propagating dependency paths among processes, enabling cycle identification efficiently. In edge chase algorithm, we have it detects deadlocks by propagating prop messages along wait for edges to find cycles. Now, centralized algorithms simply control but limit scalability. Now, distributed algorithms enhance scalability with higher communication overhead. Oh, sorry. Yeah. Coming to the deadlock recovery mechanisms, we have process termination, resource preemption, and rollback techniques. Let's go into the process termination first. It aborts deadlocked processes to break cycles, but may cause data inconsistency and will also progress. So progress might be a bit late, but still it terminates and aborts deadlocks processes to break cycles. We have resource preemption, where it forcefully reclaims the resources from deadlocked processes to break the deadlock efficiency. Next, we have rollback techniques, which takes or restores the system by aborting transactions to break deadlocks, minimizing resource wastage. Now, in coordinated recovery in distributed systems, we have consistency maintenance during recovery and synchronization challenges. In synchronization challenges, it includes maintain consistency. It avoids race conditions and control coordinating rollback timing across distributed nodes. In consistency maintenance during recovery, we see that the state updates and synchronized checkpoints maintains consistency during distribution deadlock recovery. Next, coming to the practical considerations and failure detections, or let's say future directions, because deadlock is a very common thing in coming OS, or it's a very crucial part in operating system. We see the future directions as well. For the performance optimization strategies, We see that minimization detection overhead, where it messages frequency and limit detection also. Intervals minimize overhead while ensuring timely deadlock detection or identification. Coming to the balancing detection frequency and system throughput, we see increasement of the detection frequency, reduced deadlock duration, and may lower overall system throughput. Optimal balance is essential. In emerging trends and research areas, it is mainly used in machine learning for deadlock prediction, where ML models predict deadlocks by analyzing resource allocation patterns, enhancing proactive detection and recovery strategies. In integration with cloud and edge, we have challenges and strategies for uptime deadlock detection and recovery to distributed cloud and edge computing architectures. Thank you. Now we'll be looking at the code given to us. Um, the code is, yeah, right here. Now, if I look on the code, we have distributed deadlock detection using wait for graph method. Okay. Now, let me just scroll a bit for you. Yep. Now, using collections, Python collections, I've taken up self. I know that I've initialized my graph, and for these processes, I've appended. Now, in this method, detect deadlock of self, visited as a set, and recording attack. Attack as a set. Now, in this DFS, we'll be using DFS here because we need to find the best one. So visiting add of node, and this is all the common DFS code. And now and here we have the simulation. So here's my direct detector as distribute. I've appended my main method here, main class. And now we see the example here. So the distributed dependency simulation where P1 waits for P2, it may be on site A, let's say. P2 waits for P3, maybe on site B, and P3 waits for P1. So cycle across sites. So it's a deadlock. Now, detector add dependency on P1 to P2, P2 to P3, and P3 to P1. Now, if detector detects deadlock, it prints deadlock detected among distributed processes, else print no deadlock detected. So the resulting output should be the first one, where the deadlock detected among distributed processes. Because it is a cycle detection where from P1 to P2, P2 to P3, and P3 to P1. That's it. This is a simple deadlock detection code using Python. And main DFS approach has been used here, which is using a self graph and neighbors. Thank you.